Welcome to this presentation on power systems basic concepts. Today, we'll cover the foundational elements that underpin modern electrical power systems, focusing on the key electrical properties, circuit elements, and the structure of power systems. Let's begin with some essential definitions. Voltage, volts. This is the electric potential difference between 2 points in a circuit. Current, amps. This measures the flow of electric charge through a circuit. Impedance, ohms. This is the opposition a circuit presents to current. It includes resistance, ohms, pure opposition to current. Capacitance, farads, ability to store charge. Inductance, Henry, ability to store energy in a magnetic field. Admittance, the inverse of impedance. To make the concepts of electricity more intuitive, let's compare them to something familiar, the flow of water in pipes. This hydraulic analogy helps visualize how electrical circuits work by relating them to fluid systems. Explaining the analogy. 1. Voltage versus pressure. Voltage is like the pressure in a water pipe. Just as higher pressure pushes water through a pipe, higher voltage pushes electric current through a circuit. 2. Current versus flow rate. Current is similar to the flow rate of water. It measures how much electric charge, like water, moves through the circuit per second. 3. Resistor versus restrictor. A resistor acts like a restrictor or a narrow section in a pipe. It resists the flow, causing a drop in pressure, voltage, and reducing the current, flow rate. 4. Capacitor versus diaphragm. A capacitor is like a flexible diaphragm in the pipe. When water, current, flows in, the diaphragm stretches and stores energy. When the flow stops, the diaphragm pushes water back, releasing the stored energy. Similarly, a capacitor stores and releases electrical energy. 5. Inductor versus heavy paddle wheel. An inductor can be compared to a heavy paddle wheel in the pipe. When water starts to flow, the wheel resists sudden changes in flow due to its inertia. In electrical terms, an inductor resists changes in current, storing energy in its magnetic field. Why this analogy helps? Intuitive understanding. By relating electrical concepts to fluid systems, it becomes easier to grasp how circuits behave. Visualizing circuit behavior. Just as water systems respond to changes in pressure, flow, and restrictions, electrical circuits respond to voltage, current, and resistance. Learning foundation. This analogy provides a strong foundation for understanding more complex electrical phenomena. In summary, thinking of voltage as pressure, current as flow rate, resistors as restrictors, capacitors as diaphragms, and inductors as heavy paddle wheels makes the invisible world of electricity much more tangible and easier to understand. In DC systems, voltage and current flow in one direction. In AC systems, voltage and current alternate direction at a frequency, measured in Hertz. AC is dominant in modern power systems, primarily due to the transformer, which enables efficient voltage conversion and transmission. In AC circuits, voltage and current are described as phasors, mathematical vectors representing sinusoidal quantities over time. The product of voltage and current is power, volt-ampere, VA, also a phasor. Resistive loads consume real power, watts, W. Inductive or capacitive loads consume reactive power, volt-ampere reactive, var. In DC systems, voltage and current flow in one direction. In AC systems, voltage and current alternate direction at a frequency, measured in Hertz. AC is dominant in modern power systems, primarily due to the transformer, which enables efficient voltage conversion and transmission. Here's the structure for today's presentation: electrical properties, resistance, R, inductance, L, and capacitance, C. Elements of a power system. Key power system concepts. For a resistor, voltage and current are in phase. In power systems, resistance produces heat in conductors, converts electrical energy to real power, causes voltage drops, which are critical for voltage regulation in distribution networks. Reactance quantifies the effects of capacitance and inductance using complex notation, simplifying circuit analysis. When current flows, it creates a magnetic field. A changing magnetic field induces a voltage in the circuit, opposing the change. This is the principle of inductance. The circuit resists changes in current. The voltage across an inductor is proportional to the rate of change of current. For a sinusoidal voltage, the current lags the voltage by 90 degrees. Current lags voltage by 90 degrees. No real power is consumed. Q is positive, indicating power is absorbed by the inductor. Capacitance occurs when two conductors are separated by an insulator, allowing charge storage when a voltage is applied. Capacitance, C, is the charge stored per unit voltage. The total charge moved is the integral of current over time. For a sinusoidal voltage, current leads voltage by 90 degrees. Reactive power describes the background energy movement in an AC system. It is essential for the functioning of inductive and capacitive elements, even though it does not result in net energy transfer. Three-phase systems are the standard for power transmission and commercial generation. In a balanced three-phase circuit, all voltages are equal in magnitude and 120 degrees out of phase. All phase impedances are equal. Two main connection types, Y, star, and delta. In a Y, star, connection, line current equals phase current. Line voltage relates to phase voltage. In a delta connection, phase voltage equals line voltage. Line current relates to phase current. These relationships are fundamental for analyzing and designing three-phase power systems.